Have you ever been just completely stuck? Paralyzed by choice maybe. Or just stuck in a situation like a massive traffic jam where nothing can move forward. That feeling where everything just grinds to a halt, it's so frustrating. Now imagine that exact same feeling, but inside a giant automated warehouse. We're talking millions of dollars of goods, complex processes all on the line. That's the kind of really complex, high-stakes problem we're diving into today. Welcome to the Deep Dive. This is where we take a big pile of information, maybe a dense academic paper, or like today, a groundbreaking doctoral dissertation, and we pull out the absolute key nuggets of knowledge for you. Our mission, give you that shortcut to being truly well-informed. Maybe uncover some surprising stuff, hopefully keep you hooked. So today we're plunging into the really fascinating world of internal logistics. Specifically, how intelligent robots avoid getting into those paralyzing jams, what the experts call deadlocks. Our source material is this incredibly insightful doctoral dissertation by Marcel Miller.
Exactly. And the big question we're really trying to unpack for you today is how can these autonomous mobile robots, the ones buzzing around warehouses and factories, how can they learn to navigate these super complex, always changing environments without causing total system gridlock? And maybe even more importantly, what does this kind of adaptive learning tell us about the future of automation itself? Because, it's just exploding globally right now.
That's a perfect setup. So let's start right at the beginning. We're talking about intralogistics. Now, that might sound a bit jargony, maybe.
A little bit, yeah.
But it's essentially, the internal movement, the handling of goods, information, all within a company's walls. Basically, everything that happens inside a warehouse or a factory to keep things moving. Raw materials to finished products. And just for context, this term, it was actually defined pretty precisely by the German Engineering Federation, the VDMA, way back in 2003. So it's a well-established concept.
That's right. And this whole intralogistics landscape, it's been going through this massive change. A huge driver is, a growing shortage of skilled labor, frankly, and also this critical need for automation that can actually adapt. The dissertation points this out really clearly, the number of industrial robots globally. Nearly 3.5 million in 2021. That's up 15% from the year before. It's huge growth. Companies are really moving away from just using manual labor to handle workload peaks. They're investing heavily in these reconfigurable automated systems.
And a massive part of that shift is the rise of these autonomous mobile robots, AMRs. Now, you might know their predecessors, the AGVs, automated guided vehicles. They're kind of like trains on fixed tracks, right?
Exactly, fixed paths, very predictable.
But AMRs, they're totally different. These robots navigate using sensors, smart software. They make their own decisions in real time about where to go, which is great. That flexibility is a game changer for dynamic places like warehouses. But, you can probably guess that adaptability brings its own headaches.
It really does. And the biggest headache, the one Marcel Miller's work tackles head-on, is the dreaded deadlock. So in this context, a deadlock is basically when robots block each other physically. Movement becomes impossible for at least one of them, and it just can't reach its goal indefinitely. And when that happens, it's not just one robot that's stuck. It can seriously degrade the whole system's performance, its reliability. It essentially brings everything grinding to a halt. Robot gridlock.
Okay, so if deadlocks are that critical, how did systems traditionally try to handle these robot traffic jams? The dissertation lays out 3 main strategies. First up, there's prevention. This is about designing the system layout itself so deadlocks just physically cannot happen. Think about maybe a warehouse where all the aisles are strictly one-way, like one-way streets. Robots can't meet head-on. It's very rigid, though.
Very rigid. Then you've got avoidance. Now here, the system design could technically allow a deadlock, but you use clever control rules to actively steer clear of them, maybe like a dynamic traffic light system. Controlling access to intersections or shared zones, making sure only one robot goes in at a time. It's proactive, trying to stop the deadlock before it forms.
Right. And the third one is detection and recovery. This one's more reactive. It basically lets deadlocks happen. Then once the system spots one, it steps in to fix it. Might tell a robot to back up, maybe reroute it completely to break the log jam. It's kind of like sending out the tow truck after the crash has already happened.
Yeah, exactly. And what's really insightful from the dissertation is how often the traditional ways of planning logistics systems, they kind of overlook these deadlock issues early on in the design phase. They tend to only pop up much later, during simulation testing or sometimes even when it's running live, which then means you're stuck with reactive fixes, which are often expensive and disruptive. The dissertation really flags this as a major gap. These problems should be baked into the planning much, much earlier.
Okay, so if the old ways leave us vulnerable to these costly robot jams. What's the smarter way? The more adaptive way, and this is where the dissertation gets really innovative, right? Enter reinforcement learning, RL.
Yes, RL. It's this really powerful branch of machine learning. Instead of just finding patterns in data, RL systems learn by doing, by interacting with their environment. Think of it maybe like teaching a puppy. It does something, gets a treat if it's good, maybe a no if it's bad. Over time, through tons of these interactions, it just figures out the best way to behave to get the most treats, the rewards. So RL systems develop optimal strategies or policies over time.
That sounds incredibly promising for something as dynamic and, well, messy as intralogistics. So why RL specifically? What makes it so good for tackling something like deadlocks, which seem really complex and unpredictable?
That is the absolute key point. RL doesn't just detect deadlocks after they happen. It actively learns these adaptable decision-making strategies, policies to proactively manage and mitigate them. That adaptability is just crucial when conditions are always changing, complex. Fixed rules often just break down. RL can find really clever ways to handle conflicts, ways that maybe even human engineers wouldn't think of initially. It makes the whole system much more robust.
And this connects to a really cool idea from the dissertation, doesn't it? Adding resilience as like a fourth main goal in logistics planning, alongside the usual suspects: performance, quality, cost. So it's not just about efficiency anymore. It's about designing systems to expect problems almost.
Precisely. Resilience, defined here, is the system's built-in ability to withstand disruptions, adapt to them, and recover quickly. By making resilience an explicit goal, you shift the whole design philosophy. You move from aiming for static efficiency in a perfect world to aiming for dynamic adaptability, acknowledging that the real world is messy and unpredictable. Deadlocks, for instance, they obviously hit performance through delays, they reduce quality if deliveries are late, and they drive up costs through wasted time and energy. So focusing on resilience tackles all of that head on. You build robustness in from the start.
That makes a ton of sense. Okay, so how do you actually start teaching a robot using RL? Like, what does it see? What can it do? How does it know if it's doing well?
Yeah, you have to frame the problem correctly. It boils down to three things: states, actions, and rewards. The state is essentially what the robot perceives about its environment at any given moment. This could be its own position, where its goal is, any obstacles it sees, and crucially, where the other robots are and what they seem to be doing. Now, this perception can be fully observable, meaning the robot magically knows everything about the entire warehouse grid, or, more realistically, it can be partially observable.
Ah, so it only sees its immediate surroundings.
Exactly, maybe like a little 5x5 grid around itself. Much more like how we humans see the world, right? We only see what's right in front of us, not the whole city layout.
Okay, that's the state, what it sees.
Yeah.
Then what about the actions? What choices does it have?
Actions are pretty straightforward usually. It's what the robot can do. Move up, down, left, right, or maybe choose to just stay still for a moment. Those are its available moves.
Simple enough. And the rewards. How does getting a +1 or a -1 actually teach it complex stuff, like avoiding deadlocks?
The reward function is critical. It's the feedback mechanism. So, for example, maybe a robot gets a small positive reward, say plus 0.5, the first time it reaches its assigned destination. But if all the robots manage to reach their goals in that particular task or episode, that's a big win. So maybe they all get a larger reward, like +1, and the simulation resets for the next task. But crucially, if a robot causes a collision, that's bad. So it gets a negative reward, maybe -1. This reward structure incentivizes them not just to reach their goals, but to do it efficiently and, importantly, cooperatively, without crashing or getting stuck. They learn to maximize the good outcomes and minimize the bad ones.
Okay, so that's how one robot learns. But you mentioned these warehouses have lots of robots moving in the same space, trying to reach different goals. Suddenly the problem gets way more complicated, doesn't it? This isn't just RL anymore. It's multi-agent reinforcement learning, MRL.
Exactly. As MARA, this is where the real cutting edge is and where the complexity ramps up significantly. MRL is specifically for these scenarios with multiple agents, multiple decision makers. Each robot has its own goals, but its actions directly impact the others. MRL aims to teach them how to coordinate, sometimes cooperating, sometimes maybe even competing slightly for space to achieve their objectives. The core task they're trying to solve is called multi-agent pathfinding, or MAPF, find paths, avoiding collisions, and yes, avoiding those system-killing deadlocks.
MAPF. Okay, so when we talk about robot traffic jams in MAPF, what specific kinds of jams or conflicts do they need to learn to avoid? The dissertation breaks these down, right?
It does, very clearly. You've got your basic vertex conflict. That's two robots trying to be in the exact same spot at the exact same time. Classic collision. Then there's an edge conflict. Two robots trying to use the same path segment, going in the same direction simultaneously, like trying to merge into the same lane at the same time. Then it gets trickier. A swapping conflict. Two robots trying to directly swap places. Robot A moves to B spot, B moves to A spot. In tight spaces, that can easily cause a deadlock if there's no room to maneuver around each other. And finally, the big one, the cycle conflict. This is a true deadlock. You get a chain of robots where each one is blocked by the next one in the loop. Nobody can move. That's the robot stalemate we're trying to beat.
Understanding those conflicts seems absolutely vital for teaching the robots. Okay, so how do you actually train a whole team of robots to learn these complex dances? The dissertation looked at different ways to train these MRL agents, different paradigms.
Yes, there are three main approaches they considered. First is centralized training and execution, CTE. You can think of this like having one single, all-knowing master brain controlling every single robot. It sees everything, decides everything. Great for perfect coordination in theory, but it really struggles to scale up. As you add more robots, the number of possible combined actions just explodes exponentially. It becomes computationally overwhelming, especially for real-time decisions.
Okay, so one brain for everyone is tough. What's the opposite?
The opposite is decentralized training and execution, DTE. Here, each robot is completely on its own. It learns independently, only using its own local view, its own sensors. It basically just treats all the other robots as unpredictable moving obstacles in its environment. This scales much better and works well in distributed systems, but it can be really unstable. The robots aren't coordinating. They might learn conflicting or inefficient strategies because they have no idea what the others are trying to do.
Right, like pure chaos. So is there a middle ground?
There is, and this is the approach where Miller's research found really significant success. Centralized training with decentralized execution, or CCDE. It's a hybrid. During the training phase, the robots learn together. They might share information, maybe even share parts of a central neural network. This allows them to benefit from collective experience, get better estimates of how good certain actions are, considering the whole team. But when it comes to actually doing the job, running in the real warehouse, each robot acts independently. It makes its decisions based only on its own local observations. It's clever because you get the benefits of coordinated learning during training, but you avoid that massive computational bottleneck during execution. It prevents the action space explosion while still enabling pretty sophisticated coordination.
CTDE. Got it. Okay, so how did Mueller actually put this all to the test? What kind of virtual playgrounds did these robots learn in?
The research used a set of standardized reference models. These are basically simulated environments designed to capture different aspects of real-world intralogistics challenges. They started with fairly simple conflict situations. These are small layouts specifically designed to force basic deadlock scenarios, like that classic example. Two robots needing to pass each other in a narrow single-lane aisle. One has to yield or make an evasive move. It's like a game of chicken for robots, testing basic negotiation.
Ah, right. I remember seeing diagrams like that. Blue agent, red agent, having to figure it out.
Exactly. Then they moved to more complex warehouse layouts. These included things like traditional block layouts that you see in older warehouses, but also more modern, complex fishbone layouts.
Yeah.
And critically, these often featured single-lane aisles deliberately designed to create conflicts and bottlenecks, really pushing the algorithms. They also modeled production logistics scenarios. These involve fixed locations like machines or buffer zones, where robots have to deliver parts or pick up finished goods in a coordinated way, simulating that flow from raw materials through processing to finished products.
And who are the contenders? Which algorithms did they pit against each other in these test environments? I assume they used some top ARL algorithms against the more traditional methods.
Absolutely. They chose two really strong state-of-the-art Merrill algorithms, PPO, which stands for Proximal Policy Optimization, and Impala, Importance Weighted Actor Learner Architectures. Both are known for being quite stable and effective in complex RL tasks, and they compared these head-to-head against well-known classical multi-agent path-finding algorithms. Specifically, MAA, which is a decentralized reactive approach where robots plan paths somewhat independently, and CBS, conflict-based search, which is a leading centralized approach that tries to pre-plan paths to resolve all conflicts beforehand. This setup allowed for a really clear comparison, adaptive learning versus more traditional rule-based or pre-planned methods.
Okay, the stage was set. What were the big results? The real aha moments from putting these algorithms through their paces?
Well, one of the clearest and most significant findings was that MRL, especially using that CTDE training approach, consistently outperformed the traditional methods in the complex, congested environments. And we're not talking small improvements here. In the really tough scenarios, the ones most likely to cause gridlock in a real warehouse, MRL demonstrated a much higher ability to actually find solutions and keep things moving. For example, there was this one particularly nasty layout called dead ends. Really tricky. PPO, trained with CTDE, achieved a 100% success rate. It always found a way for all the robots. MAA, the decentralized classical method, only managed 23% success. And CBS, the centralized classical one, only 33%. That's a massive difference in reliability when things get tough.
Wow, 100% versus 23 or 33%. That's not just better, that's transformative for those hard cases.
Yeah.
So CTDE really was the key for MRL's success.
It seems so. Both PPO and Impala, when trained using CTDE, showed the fastest learning progress and the most stable performance. They consistently achieved the highest average rewards across the board, especially as the scenarios got more diverse and complex. Now, it's true that sometimes, in very simple, uncongested situations, the classical algorithms might find a slightly shorter path, mathematically speaking. But the crucial difference was that in the challenging scenarios, the classical methods often failed to find any path at all. They just gave up. MRL, on the other hand, almost always found a solution, even if it wasn't provably the absolute shortest. That robustness, that ability to just find a way, is exactly what you need in the real world.
Okay, robustness is key. But what about scale? Real warehouses might have dozens, maybe hundreds of robots eventually. Does MRL hold up when you add more and more agents? Does it just fall apart?
That's a critical question, scalability. And look, any method will eventually struggle as you add more robots. The problem inherently gets exponentially harder. But the research showed that the ORL algorithms, PPO and Impala, scaled much better than the traditional ones. For instance, in one specific warehouse model, MAA completely failed. Couldn't find any solutions at all once they went beyond 8 robots. But PPO was still achieving high success rates even with 14 or more robots in the same environment. So while there's still a limit, MRL seems to handle higher densities much more gracefully. It shows a significant advantage for busy, high-throughput systems.
That's really promising for future applications. What about dealing with new situations? If you train these robots in one type of warehouse layout, can they adapt if you deploy them in a slightly different one they've never seen before? Or are they stuck?
Yeah, that's the generalization question, and it's super important for practical use. And the research had a really key finding here. Generalization is significantly improved by training on diversity. They found that training the MRL policies on a mix of different layouts, exposing them to various types of challenges during training, made them much better at handling completely new, unseen layouts later on. And this was achieved even with the same total training time or budget. So smarter training, more varied training leads to smarter, more adaptable robots. They're not just memorizing paths for one specific place, they're learning underlying principles of navigation and conflict resolution.
And this wasn't just all theoretical grid world stuff, right? I think you mentioned they checked this with other software too.
That's right. They validated the core findings using a sophisticated industry-standard simulation tool called plant simulation. This helped confirm that the MRL approaches have real potential for actual production logistics systems. It showed they could handle more realistic complexities, including things like AGVs having to reverse down single-lane tracks, which is a common but tricky maneuver in real facilities. It helps bridge that gap between the academic models and potential industrial application.
Okay, so wrapping this all up, what does this deep dive into Muller's research really mean for you, our listener? Whether you're maybe a logistics planner, an engineer, or just someone curious about where AI and robotics are headed.
Well, for anyone involved in logistics planning, I think the big takeaway is that thinking about deadlocks and resilience more broadly isn't just some minor technical detail you fix later. It's actually a core strategic issue that directly impacts system performance, reliability, and cost. Integrating something like reinforcement learning into the planning process means shifting from designing static, rigid systems to creating dynamically adaptive ones, systems that can learn, respond, and keep working even when things get messy. It's about designing for adaptability from day one.
Yeah, and just imagine the power of digital twins in this context. You're not just using a digital model to check a layout anymore. You could use these incredibly realistic simulations as, like, training grounds, training these intelligent robot policies to learn how to dodge traffic jams, how to recover gracefully, all safely in the virtual world before you deploy anything physically. It's like having a continuous risk-free boot camp for your robot fleet.
Absolutely. Now, the road ahead for MARL, it's definitely promising, But we should be realistic. There are still challenges. Training these complex models, especially for very large systems, can require a lot of computing power and time. That's still a hurdle. And ensuring that what works perfectly in simulation transfers flawlessly to the real world, especially when robots might have imperfect sensors or unexpected things fail, that's still an active area of research. We need more work on maybe transfer learning to speed things up and ensuring long-term robustness when things get really unpredictable.
This whole discussion reminds me of that old paradox, Buridan's ass. The donkey stuck between two identical bales of hay, unable to choose and starving to death, paralyzed by symmetry. But what we're seeing here, by shaping behavior through these learned rewards, is systems that break that paralysis. They learn to act with purpose, turning potential stasis into dynamic, effective movement. Imagine logistics systems that move, not just because they're following rigid, pre-programmed rules, but because they've actually learned the best way to navigate and adapt in their specific environment. They move because they know how, not just because they were told to.
It really is a fundamental shift in how we think about automated systems, and it makes you wonder, doesn't it? What other complex systems out there in your life, in the world, could benefit from this kind of adaptive, learning-based approach? How might AI like this change how we manage city traffic, or global supply chains, or maybe even how we approach our own daily routines and decisions?
Lots to think about there. That's our deep dive for today. Join us next time for more nuggets of knowledge.